Today is the last lesson for this half of the chapter. So I'll talk about this more after the test, obviously, when we start 2.6, but it's almost like when we start 2.6, we're resetting. We actually go back to the tangent and velocity problems, but we start to define what a derivative is. And there's two main parts of calculus. There's differential calculus, the study of derivatives, and then integral calculus, the study of integrals. So you'll see how limits tie into derivatives once we get there. But for today, another reminder, you will have a homework quiz tomorrow, and that will cover anything from this week. So Monday we covered 2.4c, that was the intermediate value theorem. Yes, you would need to know the intermediate value theorem. And then we covered 2.5, Tuesday, Wednesday, and today, limits involving infinity. And today is specifically infinite limits at infinity. So now this is where not only could your limit equal positive or negative infinity, but x could be approaching positive or negative infinity as well. So it's almost as if when x approaches infinity, y also approaches infinity, or some combination with positive and negative infinity. So this is the notation for it. X could approach either positive or negative, and then your y values would also approach positive or negative. Again, this is a limit then that would not exist because it's approaching positive or negative infinity, but it's just describing the way in which it doesn't exist. So I have three limits listed directly below that key box that's there. Three functions that represent this definition of an infinite limit at infinity. So if you take the limit as x approaches positive infinity of e to the x, we looked at the limit of e to the x yesterday when x is approaching negative infinity, but this graph, I'm just sketching the graph of e to the x. So as x approaches negative infinity, if you're looking at the leftmost part of the graph, those y values approach 0. If x is approaching positive infinity, your y values become infinitely larger and larger, so your y values also approach positive infinity. So that would be one example of this type of limit. Another example would be if you have the limit as x approaches infinity of x cubed. And you can think intuitively about this as well. If you're taking an infinitely large number and then cubing it, it's going to still be infinitely large. So this approaches infinity as well. But you could tie that into or relate that to the graph of x cubed. So if your x values are getting infinitely large, so are your y values. If your x values are getting infinitely large in the negative direction, so do your y values. So that's actually the next one here. This would be negative infinity. And you can think of that too if you take a very large negative number, which yes is actually a very small number, but a very large negative number and then cube it, it's going to be even more large and negative. So you can think about it that way as well. So here in these three examples, this is actually the process we went through yesterday. I would like you either individually and then compare as a group or in your groups to work on these three and find these limits. And then we're going to go through them and discuss more with them. But the process is the same as what we talked about yesterday if x is approaching infinity, and it's what we just reviewed too with the homework examples I just went through. You just don't have radicals. So go ahead and find the values of those three limits, and then we will discuss them and come up with some generalizations is our goal. What? Generalizations? There's a trick.
Actually, no. Are we doing the first one? First four.
You are right. But this is yes. Yes. So we're gonna talk more about the common sense. This next one was always drive by the highest common denominator. That is the highest common denominator.
Oh, yeah. Yeah, they're pushing. Yeah. No, yeah. Yeah, but I didn't remember. They're not pushing zeros. They're pushing five to like say 10,000. No, but one negative, negative, pushing negative. Too much fire. Oh, it's not negative square. Number one approaching one. Why is this no question? Oh, okay. Oh. I'm on number one still.
All right. I think from what I saw, I think we're okay at least with the first two. Just double check. Your first one should be -4/9. Thank you. There you go. -4/9. Are we okay with the first one? Okay. The second one should be 0. You would get 0/1, which is 0. And then I will go through the third one. So I'll go through this whole process, so in case you did have some questions on the first two, the process is still the same. So you always, whenever x is approaching either positive or negative infinity, you always divide every term in the top and the bottom by the highest power in the denominator. So not just the highest power that you see, but it has to be in the denominator. So we divide everything by x squared in this case. So I'll have the limit as x approaches negative infinity of, and if I divide 3x to the 7th by x squared, I'm going to have 3x to the 5th. And then minus 4x squared divided by x squared will just be 4. And then plus 1 divided by x squared. And then in the denominator, I'm dividing 5 by x squared minus, and 10x squared divided by x squared is just 10. So anytime you have a number divided by x to a power, this approaches 0. Because you're going to have a number over something very, very large. It's going to be a number very, very close to 0. So that means, now if I am thinking of x being a very large negative number, if I were to substitute in a large negative number for x, raise it to the 5th power, it's still really large and negative. Multiply it by 3, it's still really large and negative. So this term is approaching negative infinity, some very large negative number. And then I know 4 is just approaching 4, and then 10 here is just approaching 10. So I end up with essentially negative infinity minus 4 divided by negative 10. So if I have a large negative number and I subtract 4, it's still large and negative. And then when I divide by 10, it's still large, but I'm dividing by a negative, which makes it now a positive number. So this limit is positive infinity. You don't need to put a plus sign. But it should not be negative because you're dividing by the negative 10. Does that help for the third one? Okay. Now, what I want to generalize with this, there is a sort of shortcut for these. I know. Well, the process itself isn't terrible, but there's a shortcut. Take a look at the first one. Look at the limit. The limit's negative 4/9. Do you see a negative 4/9 in the original problem? There's your negative 4/9. So I could look at that problem and without doing any work tell you it's going to be negative 4/9. Notice though, the highest power in the numerator is the same as the highest power, or the highest power in the denominator, sorry, is the same as the highest power in the numerator. So if you have the same degree, because remember rational functions, they're polynomials on the top and the bottom. If the degree of the numerator is the same as the degree of the denominator, then the ratio of their coefficients is your limit when x approaches positive or negative infinity. Okay? Now, that doesn't mean you don't have to do the process. This is not something that you should say, well, if you're kind of second guessing, like, I don't know if I'm going to remember that, you don't have to remember it, okay? This is just something, it's a sort of shortcut. If you do remember it, it's something you can use. Otherwise, do the process that we learned. Take a look at this second example. What do you notice about the degree of the top versus the degree of the bottom? The degree is larger on the bottom. Anytime, and it doesn't matter what the difference in the degree is, if the degree is larger in the denominator and x is approaching positive or negative infinity, your limit's always going to be 0. And that's because if you're dividing everything by the highest power in the bottom, everything on top is going to approach 0 because it's going to be something over x. And then what about the degrees for this one? Higher on the top. So if you're dividing by the highest power in the bottom, you're still going to have a term that is x to a power on the top. And so your limit will either be positive or negative infinity. And you kind of have to reason through what you think it's going to be in terms of positive or negative, but it's going to be one of the two infinities. Yes. Yep. If the higher power is in the denominator, it's always 0. When x is approaching positive or negative infinity. So yes, this will be something I'll remind you of when you're reviewing. First of all, the method you use to find these limits, and now these shortcuts only apply if x is approaching positive or negative infinity. Don't start applying these methods if x is approaching 2. Then those methods don't work. So, are there questions on that? It's kind of a shortcut or way to reason through it, but not that it has to be used, just something to notice. Okay, then the next example, I saw some of you were working ahead, so just kind of make sure that what you're doing is correct. I'm going to show you what you are not allowed to do for this example. The limit as x approaches infinity of x squared minus x. You cannot, so I'm going to write it, but I'm going to write it as like you cannot do this. You cannot apply limit laws here and say Well, this is going to be the limit as x approaches infinity of x squared minus the limit as x approaches infinity of x. And then I know when x approaches infinity for x squared, I'm squaring a very large positive number, so that's going to be infinity. And then subtract the limit as x approaches infinity of x. Well, that's going to be infinity as well. And infinity minus infinity is 0. Well, don't think to do that, because that doesn't make sense. You can't look at this and basically say, okay, if I plug in infinity, I'm going to get infinity minus infinity, and that's 0. This is not true. Infinity minus infinity, by the way, this is something that's not technically defined. There are different sizes of infinity. Yes. It's from a movie, isn't it? But yes, some infinities are greater than others. Yeah, it's from a movie. But yes, there are different sizes of infinity. That's getting into a whole different conversation that we don't need to get into in calculus. But there are different sizes. So how to work through this one, since this is not something you should do. Instead, you should find a way to rewrite this expression, x squared minus x. Yes, so we could factor it. We don't want to use conjugate. That's more specific if you have, square roots, yep. So I am allowed to apply limit laws if I factor this and think of it this way. Now I can think of it as I'm taking the limit as x approaches infinity of x, and I'm multiplying by the limit as x approaches infinity of x minus 1. Here this is defined, and this does make sense mathematically. So if x is approaching something very, very large, the limit of x is going to be infinity, that very, very large number. And now as x approaches infinity, x minus 1, well, that's a very, very large number minus 1, which is still large, so that would still approach infinity. And I can reason that if I multiply two very, very large numbers, it's still very, very large. So this limit is infinity. Infinity. Why? Well, you could say the y values are infinite. Like as x approaches infinity, the y values become infinite. If you're just, the way I would read this is I would say the limit as x approaches infinity is infinity if I was reading it that way, or I would say the y values become infinite. I would say that. Typically, the conjugate helps you most if you have square roots in the expression. If it works, I don't see why that wouldn't work in every case, but this would be, I guess this would be a more efficient way to get to the answer, is rewriting it this way. Conjugates, there isn't a way to rewrite an expression that would have a square root, which is why we do multiply by the conjugate. If you did that and you got the same answer, like I said, I don't see why it wouldn't work every time, but this would be more efficient. Your way is not wrong. So if you did that and everything was correct, then it's fine. Yeah. All right, any other questions with that example? Okay, and then the last one, so this is one that we didn't talk about any of this today, but over the last couple days we looked at infinite limits, helping us find vertical asymptotes, and then limits at infinity. We didn't go through an example, which is why I included it on here, but being able to use those to find horizontal asymptotes. And I have here to find all of the asymptotes without graphing it on your calculator. So you would need to know how to justify that there are asymptotes without actually being able to graph it. So if we start out with finding the vertical asymptotes, set the denominator equal to 0, so you have to kind of find where there could be a vertical asymptote. So I talked about it as being the candidates for a vertical asymptote. So this would be where x squared minus 1 is equal to 0. Yep, so where x squared would equal 1, which would be at positive 1 or negative 1. And then to actually justify that there is an asymptote there and not just a hole in the graph, you have to find the limit as x approaches each of those values from at least one side. So if I find the limit as x approaches positive 1, and I'll approach it from the right side, of 3x squared plus 4 divided by x squared minus 1. I know I'm going to get 0 in the denominator. In the numerator, I get if I approach 1, I'm going to get 7. Right, 3 plus 4. What? It's always positive on top, yes. And yes, well, yeah, because you're squaring it. Yep, yes. So it's going to approach infinity, but this alone shows that x equals 1 is a vertical asymptote because that limit approaches infinity. So I can say, therefore, x equals 1 is a vertical asymptote. And then find the limit as x approaches negative 1. Again, from just one side is all you have to show. So the top is still going to approach 7. Right. So, was that what you were saying between positive and negative 1? It's going to be positive either way. Yeah. So then this would be positive infinity as well. And therefore x equals negative 1 is a vertical asymptote. Well, let me think about this one actually. If I plug in a number that's close to negative 1 but larger, yeah, so like I'm thinking negative 0.5, that squared is smaller than 1. When I subtract 1, this is going to be negative. I mean, it's still an asymptote, but yes, it would approach negative infinity. So yes, it's still an asymptote, but you want your justification to still be mathematically correct. So up here, though, if I'm approaching 1 from the right, so a number bigger than 1, that denominator would still be positive. Okay. Are there questions on the vertical asymptotes? Now, it depends on the function how many candidates you actually have to check for with a vertical asymptote. Horizontal asymptotes This was actually one of the practice questions. What is the maximum number of horizontal asymptotes a function can have? 2. So it can either have 2, just 1, or it doesn't have to have any. So for a horizontal asymptote, there's only 2 limits you actually need to find to check for a horizontal asymptote, and that is the limit as x approaches positive infinity of your function and the limit as x approaches negative infinity. Now, I won't say every time, because it is possible for a function to have 2 horizontal asymptotes. I won't say every time that these 2 limits are the same, but oftentimes they are the same because you solve them the same way. But I'm thinking more if your function was something like arctangent or inverse tangent, then these 2 limits are different. But ultimately with rational functions, a lot of the times these limits are the same. You should still show that both of them are the same though. Or, you know, if something ends up being different. But these you would solve just like we did the 3 on the front. Try without using the method, look at your function, what's the limit going to be? 3. Your degree is the same in both numerator and denominator. Ratio of coefficients is 3/1. So these limits are both 3. So you still need to show both. You need to show that you are considering both limits, but together this means that the line y equals 3 is a horizontal asymptote. So there's just one. Also, if these limits are positive or negative infinity, that means there is no horizontal asymptote. So that third example of those 3 on the front that I had you work on that was equal to positive infinity, that would mean there isn't a horizontal asymptote.